Have you ever stopped to wonder what's actually going on inside an AI's mind? I mean, really going on. Well, it's not some unknowable black box of magic. It's just math. Really elegant math, actually. And today, we're going to pull back the curtain and break down the exact engine that makes it all work, step by step.
Yeah, that's the big question, right? We see these things creating incredible art, answering complex questions, but how do they get there from basically nothing? I promise you, it's not magic. It's a surprisingly beautiful process, and it all boils down to one simple idea. I want you to picture this. You're standing on the side of a huge mountain, but you're in a super thick fog. You can't see a thing. Your goal is to get to the very bottom, the lowest point in the valley. The only thing you can do is feel the ground right under your feet to figure out which way is downhill. That's it. If you can wrap your head around that one idea, you're already halfway to understanding how all of this works. Seriously. Okay, so where is this foggy mountain? Well, it's a virtual mountain, and it exists inside something we call an artificial neural network. This is the AI's brain, if you will. It's the fundamental structure for everything we're about to talk about, and it's even inspired by the way our own brains are wired. You know how our brains are made up of billions of tiny neurons? Well, these models are built from artificial neurons. Think of them as tiny, simple calculators that are all connected in this massive web, organized into distinct layers. Data just flows through this web, getting tweaked and transformed at every single stop along the way. Right. So to really understand the big picture, we actually have to zoom way, way in. We need to look at the single most important building block of this entire system, one single artificial neuron. First things first, everything starts with data. We call this the input, or X for short. This is just the raw information we're feeding into the system. So, for example, if you give it a picture of a cap, the input is just a giant list of numbers, one number for the brightness of every single pixel in that image. Now, this is where it gets really interesting. We have something called a weight. The best way to think about a weight is like a volume knob or a dimmer switch. Every single one of those pixel values gets its own knob. And this knob tells the neuron how important that specific pixel is. Is this pixel part of the cat's ear? Turn the knob way up. Is it just some boring background? Turn it way down. The entire learning process is just the network figuring out how to set millions of these little knobs perfectly. And it's not just the weights. There's another piece called the bias. You can think of the bias as the neuron's, its starting mood or its default opinion. It's just a number that makes the neuron naturally more or less likely to get excited and fire off, even before it looks at any of the inputs. So here's the core calculation. It's super simple. The neuron takes every input number, multiplies it by its importance knob, that's the weight, and then adds all of those results together. At the very end, it adds in its own little opinion, the bias. That's it. That one little piece of math is literally the heartbeat of the entire network. Okay, but wait. That calculation just spits out a number, right? And a number isn't a decision. It's not a yes or a no. So how does the neuron take that number and decide, all right, I'm going to fire and pass a signal on to the next guys in line? Well, that's where the activation function comes in. And this step is so important. It takes that final number and runs it through one last little function. Now here's the key. This function has to be nonlinear. And I know that sounds like jargon, but it's the secret sauce. Without it, a giant network with 1,000 layers would just mathematically collapse into one simple, boring equation. It wouldn't be able to learn anything complex at all. And there are a couple of popular ones. You've got ReLU, which is super simple. If the number coming in is negative, it just outputs 0. The neuron stays quiet. Done. Then you have something like Sigmoid, which is great because it takes any number, big or small, and squishes it down so the output is always between 0 and 1. And that's perfect when you need your output to be a probability, right? Like, I'm 98% sure that's a cat. All right, so that's our Lego brick. That's the neuron. Now let's zoom back out and see how we stack millions of these things together to build something really powerful. So, a basic network has 3 main parts. First, the input layer that just takes in the raw data. Then you have the hidden layers. This is where the real magic happens. All those neuron calculations we just talked about happen over and over again in these layers, letting the network find more and more complex patterns. And finally, you have the output layer, which gives us the final prediction. Okay, now for the really, really cool part. We have the structure, but how does it actually learn from its mistakes? It all comes down to this really elegant and dynamic cycle. The entire learning process is basically a 4-step dance that just repeats over and over. Step 1, the network makes a guess. Step 2, we measure how wrong that guess was. Step 3, we trace the error backward to find out who was responsible. And step 4, we adjust all the knobs to do better next time. Let's walk through that. So forward propagation is exactly what it sounds like. We feed our data into the first layer, and it flows forward all the way through the network, with each neuron doing its job until the final layer spits out a prediction. This is the network's initial guess. So how good was that guess? To figure that out, we need a loss function. It's just a formula that compares the network's prediction to the actual correct answer, and it spits out a single number that tells us the total error. The goal of all this training is to make that number as small as possible. Now, this is the true genius of this system. It's called backpropagation. Using a clever bit of calculus called the chain rule, the algorithm works its way backward from that final error number. It calculates precisely how much each individual weight and bias in the entire network contributed to the mistake. It's like a perfect system for assigning blame. So backpropagation tells us exactly who to blame for the mistake. Now, gradient descent is how we actually fix it. Using this formula, we take every single weight and bias, every single knob, and we give it a tiny nudge in the direction that will make the error smaller. And look, we're back to our hiker in the fog. This is the perfect analogy. The loss function is the shape of the mountain. The network can't see the whole landscape, but it can feel the slope right where it's standing, and that slope is the gradient. So it simply takes one small step in the steepest downhill direction it can feel, over and over and over again. And that little alpha symbol in the formula, that's the learning rate. It's just the size of the hiker's step. And getting this right is super important. If the steps are too big, you risk jumping right over the bottom of the valley. But if they're microscopically small, the journey to the bottom is gonna take forever. Okay, so we've put all these pieces together. What does training actually look like in practice? Let's talk about how we handle huge data sets and a major pitfall you absolutely have to avoid. You can't just feed a network a massive data set all at once. That's like trying to memorize a whole book in one go. So instead, we break it into smaller batches, like reading one page at a time. The network learns a little from each page. And when it has finally seen the entire book, we call that one epoch. But there is a serious risk here. If you train for too many epochs, the model can start to overfit. It's like a student who just memorizes the answers for a test without actually understanding the concepts. The model performs perfectly on the data it's already seen, but it fails miserably when you show it something brand new. And there you have it. From the simple math of a single neuron to the grand looping dance of gradient descent, we've seen how a mind can be built from numbers. A mind that learns, adapts, and improves one tiny calculated step at a time. The foundation is laid. The only question now is what we'll teach it to do next.
Like and subscribe for Simplify Tech, explaining one concept at a time, simplifying the technology and AI.